Welcome to our 31st session. In today's session, we're going to continue our discussion of the metal oxide semiconductor capacitor, also known as the MOSFET. We're going to review a little bit of what we did last time, go on to talk about threshold in a qualitative way, discuss capacitors in series, and specifically the depletion capacitance, and then we'll take our first stab at subthreshold inversion, and we'll look at something called the CV plot, the capacitor voltage plot, which we saw a little bit in the PN junction, and if we have time, we'll do a summary of semiconductor structures. But first, the Blue Danube with a marvelous performance by Andre Roux, and we'll see you in about 6 minutes. Okay, welcome back, and here are the topics that we'll be covering in today's session. We're going to be doing a little bit of a review, talking a little bit about threshold, only qualitatively. We'll have a lot more to say about that in the future sessions. Then we'll be discussing adding capacitors in series and talking a little bit about the CV plot, the capacitor voltage plot. That's something we'll be using quite a bit in our MOSFET and our MOSFET discussions, talking a bit about the depletion capacitance, and then again, only qualitatively, we'll be talking about subthreshold, that region from where we get intrinsic, where the Fermi level crosses the intrinsic level, up to the strong inversion level. And then we'll be doing a few things like summary of the Schottky PN junction, PN rectifying junctions. Again, we know, remember that Schottky could be either rectifying or non-rectifying. Generally, the rectifying is the more important. Then we will go on to a summary of semiconductor structures. I don't know if we'll do this really all that deeply. It's all there in the text, so I'll just perhaps touch on some of the highlights. And if we have time, we'll talk about some more summaries and numerical examples, and we'll continue that probably in our next session. And then we'll end with a video clip, which I think you'll find kind of nice. So that's at the end. Okay. Anyway, so in matter of review, the MOSFET, the metal oxide semiconductor capacitor, which is composed of an oxide layer capacitance and generally a depletion layer capacitance in the silicon, and in the MOS cap, we have a number of regions. We can vary the external bias in NMOS with a P-silicon substrate with a negative bias in accumulation, and then we go to flat band, and then we go to depletion, and then we go to subthreshold, right in this region here, and then subthreshold inversion, and then strong inversion, which for voltage is more positive than the threshold voltage. Now I've made a blue region in here which shows the possible variation of external bias in the metal semiconductor, in the Schottky. And you see it's really the same kind of structure, but the range is much less. It can only basically be in depletion, and as we make the voltage, say for P-type silicon, more negative, we don't get to flat band. This is forward bias, and we get a large forward current. In this region here, we have reverse bias, and we get a reverse current. So the range of external biases is much smaller. And I suppose also in the way of review, threshold purely qualitatively, as the gate voltage increases in magnitude, more positive for NMOS, and this is the one we'll be concentrating on. The band bending increases such that the Fermi level falls below E sub I. Here's Fermi level, actually, I should say E sub I falls below the Fermi level. So right at this point, we start weak inversion, and then we continue to increase the magnitude of the gate voltage in a positive sense, such that we get to a point where this distance right here, which we call this, for want of a better term, I can call the surface band bending, is equal to the bulk up here. So when this distance here becomes equal to this distance, we get strong inversion. And that's basically what we're saying here. And the rationale was when we get to strong inversion, we have so many electrons. We have such a high density of electrons at the surface that they shield the depletion region, and we get no more band bending. So that's a criteria for strong inversion or threshold. We get no more band bending in the depletion region. And those results are summarized in this figure here. We derived this equation in our last expression. It took a bit of work, and I can tell you that the amount of information contained in this expression is not all that great. It's like I used to say, my parents went to Paris and all I got was a t-shirt. So this is the t-shirt. It's not as much information as we'd like, but there is a fair amount of information, and it shows that there is band bending in the depletion region, which basically stops at inversion. This is one of the problems right here, because it is it's a corner. It's a sharp point. Sharp points are not very good. So flat band we're going to be working on. We'll do a lot more work, but we'll get a lot more information. In the flat band, of course, Vg is equal to Vfb, so this term goes away, and you can see that the band bending will go to 0 because we have 1 minus 1. So all this goes to 0, and the phi sub s goes to 0. The point right here is that we can expand that out close to flat band, but a little bit greater. So Vg is a little bit greater than flat band. This term will be very small, and if this term is very small, we can expand out this square root, and it's equal to approximately 1 plus what is this term, this small term here, divided by 2. And we saw that, or at least we stated that in our last session. That's a relatively straightforward expansion. So if we do that expansion, we find immediately that the band bending is parabolic in Vg. So that is basically what we're saying here. And in fact, it's parabolic for gate voltages close to and a little bit greater than flat band, and then it levels off. Now we could probably, if we wanted to do a lot more work, we could find out what this point is by simply taking the derivative of the phi sub s with respect to Vg and setting the derivative equal to 0. I may have done that in some of my worksheets, but it's not a very pleasant thing. And we'll be doing this in a much more comprehensive way, so I don't think it's particularly useful to show that here. Okay, we mentioned previously that adding capacitors in series is important for the MOSFET simply because we do have two capacitors in series, the oxide capacitance and the depletion capacitance. So we want to know how to add them. And we've indicated here on this drawing two capacitors. They're connected in series. The region in red is an equipotential because they are shorted together. So the potential here must be equal to the potential here. So we show that as one big metal, and what we're saying is that this is a short. There's no field in here. However, there are surface charge densities. In the left region, it would be negative, and in the right region, surface density would be positive. Okay, so that is indicated in this diagram here, 1718. So these are induced surface charges at the two ends of this equipotential field-free region. And well, so it's an equipotential, and we take it away. Just get it out of there. And then we have this diagram here, which is completely equivalent to this, of the width is equal to W1 plus W2. Here we have W1, here we have W2, and this diagram we're just showing that as W1 plus W2. So these are completely equivalent. This figure here is completely equivalent to this figure here. This is W1, probably should have put it in, and this is W2. So now we've got everything we need. And we just say that the capacitance C1, which is the capacitance here, sorry to go back and forth, this is C1 and this is C2. We can write those capacitances out. And then again, these are not aerial capacitances because CV plot we actually measure capacitance. So we stick the cross-sectional area in. It's probably not very important. It's just the length times the depth into the picture. It's just equal to, of course, epsilon A divided by W1. C2 is epsilon A divided by W2. But the total capacitance here is, well, same thing. It's epsilon A divided by the total width, which is W1 plus W2. And since they are equal, we can equate them. And it's better basically just to flip them because in that case we can just add the denominators easily. And we add the denominators and we get 1 over the total capacitance is the total width divided by epsilon times the cross-sectional area. And what we're saying here is that if we take 1 over C1 plus 1 over C2, we get 1 over C total. So we see, and this is really the critical part of this, that the capacitance is dominated by the larger W. The larger W is, that's the bigger total capacitance. And that adds, capacitors in series add just like resistors in parallel. Resistors in parallel, the resistance is dominated by the larger of the two resistors. Is that true? Larger or smaller? Let's see. If we have two resistors in parallel and one of them is very small, then the resistance is very small. So I should have said resistors in parallel, their total resistance is dominated by the smaller of the two resistors, and capacitors in series, the total capacitance is dominated by the smallest, just like resistors in parallel, the smallest of the two capacitors. And again, this is just a kind of a reiteration of everything we've been talking about here. The MOS structure, we've got two capacitors. The total capacitance is dominated by the smaller. So we ask the question, which one would we like to be smaller? Well, I think it's pretty clear. We would like the depletion capacitance to be the smaller. We want the oxide capacitance to be as large as possible, which means that we want the oxide thickness, which we're going to call T-ox, T for thickness, ox for oxide. We want T-ox to be as small as possible. And in this short section, I'd like to just highlight some of the differences between depletion capacitance and regular parallel plate capacitor. The regular parallel plate capacitor, like up here, we have charge confined to the surface regions on the right and the left side. Since the left side is made positive, we have a positive surface charge density on the left side, and a negative charge density on the right side. That's not true in depletion capacitors, because in depletion capacitors, the charge is spread out over the depletion region. It is constant generally, unless we make it non-constant, but the charge is not confined to the surface. Only in the two regions of accumulation and strong inversion do we have charge confined to the surface, in this case, the surface of the oxide. So that's certainly one difference. And of course, the fact that depletion capacitance has this charge spread out over a region is similar to both the p-n junction and the Schottky barrier. In a parallel plate capacitor, we have the ability to store charge even when the capacitor is disconnected from the source, and that's a big deal. That's why when one walks into an ion implanter, you've got to have a shorting bar, because ion implanters have lots of capacitors. Even when we pull the plug, the voltages can be quite lethal. Depletion capacitance, depletion region capacitors do not store charge. So when they're turned off, they are off, and the depletion region goes away, and the charge becomes covered up with mobile either electrons or holes. The other thing about depletion capacitors, we generally don't measure the total capacitance, but rather the differential capacitance. What we do is we apply a voltage, gate voltage, and then we apply a little bit more. So we have charge which is stored in the depletion region, and then we apply a little bit more, and we see how much more, how the voltage, how much charge we get for a little bit of an increase in voltage being the independent variable here. And of course, Q is equal to CV, so dQ dV is equal to this differential capacitance. We change the voltage a little bit. We look at how much charge is added or subtracted, and that is represented by this probably should be a delta W, by a little bit of a change, or W plus delta W, a little bit of a change in the depletion width. And that is indicated here. We apply DC bias, which sweeps. We go from accumulation to depletion to inversion. So it sweeps all of the different areas, and then we apply a small AC signal. We wiggle the voltage a little bit. We superimpose it on this DC bias. So, for example, if we're in depletion, we apply a little bit of AC bias, and we see how the depletion region changes, how it reacts to this little bit of bias. We have to have a DC bias, because the DC bias puts us in depletion, where we want to be. Okay. So, for example, in an NMOS structure, a negative bias brings us into accumulation generally, which is not such a big deal, but really be like a positive bias, bring us into depletion, and then we can measure the differential capacitance. Okay. So now let's talk a little bit about this subthreshold region, or the subthreshold inversion region. And let's look at the MOSCAP, the MOS capacitor. Notice that the bands bend in the oxide in the same direction that they bend in the silicon, and that's because they're passive elements. In this particular case, E sub I falls slightly below the Fermi level at the surface, so we have some electrons in this region. We have a large number of fixed negative ions in the depletion region, so we have a fairly healthy depletion width. However, the band bending here is much smaller than the bulk band bending by sub B. And again, the critical factor in all of this is the relationship between the intrinsic level, E sub I, and the Fermi level. So as we move into depletion, the bands bend down. They always bend down for P silicon. We should be familiar with that. And what happens when we get into depletion, the capacitance goes down. Now, accumulation, there was no depletion capacitance. There was just one capacitor, and it's the regular, it's epsilon divided by, or epsilon A divided by the oxide thickness, T ox. But as soon as we pass the flat band voltage, we start adding in this capacitance here. Well, this capacitance becomes the smaller of the two. So the smaller of the two starts to dominate, and the total capacitance decreases. And it continues to decrease as this capacitance becomes smaller and smaller and smaller as W becomes bigger and bigger and bigger. And this is the CV plot. By the way, this axis can be any place. What is the position of this axis? It depends on the work function difference. So it's not really important that it be in depletion or in accumulation or whatever. And what happens is that this capacitance, the total capacitance, will continue to decrease as the intrinsic level falls further and further and further until we get to threshold. And when we get to threshold, all of a sudden, this capacitance now is shielded by this large surface charge density of electrons. The total capacitance will jump back up to Cox. And I've indicated this is an NMOS structure. So for negative voltages, generally we have accumulation. And for positive, we always have accumulation for negative gate biases in NMOS with a P-type silicon. And again, what happens at threshold, this is going to jump up. And that is shown right here. So what we have is, this is just a continuation of this diagram. Somewheres in here, there is a point where the intrinsic crosses E sub F, and that's the start of weak inversion. And at that point, the total capacitance starts to level off, and the reason is because we're shielding the depletion capacitance with negative electron surface density at the oxide silicon surface. And we get to threshold, it's completely shielded, and the oxide now dominates completely, and the total capacitance becomes Cox. So if I'd really drawn this accurately, these two levels here should be precisely the same. I made this perhaps a bit too high. And again, this is for NMOS. For PMOS, it's exactly the reverse. So we have accumulation here. We have flat band here. The red, this is flat band. We have depletion. We have the onset of weak inversion. We have threshold at this point, and this capacitance again jumps up to Cox. So I probably should have labeled this. This diagram is for PMOS, N-type silicon. This one is NMOS, P-type silicon. This region here is the bad boy. That's what we like to minimize as much as possible, and we learn about, not right now, but we'll learn about a little bit later on, a figure of merit, which is called subthreshold swing S, which measures the ratio of Cox to C-dep. C-dep is the depletion capacitance, Cox being the oxide capacitance. And we'll find that the smaller S, the better we have, and S is measured in millivolts per decade, and 60 millivolts is the theoretical limit. Okay. Let's do an example now. Consider an NMOS, which is P substrate, MOS cap, doped with our standard doping of 10 to the 17th. It's got an N plus polygate, which means that the work function for the metal, this is the metal, don't forget, it could be aluminum or it could be N plus, or it could be N plus plus. I don't know why. Sometimes I use plus and sometimes plus plus. It's a generally doped polysilicon for the metal. And the oxide thickness is 34.5 angstroms. Why do I use 34.4 angstroms? Because it gives a nice number for the C oxide of 10 to the minus 6. This is a relatively thin gate oxide. So just to give you an idea, this is about 35 atomic layers. There are 10 angstroms per nanometer. Therefore, there are, well, we know that there are 10 to the 9th nanometers per meter. That's 10 to the 9th is 1 billion nanometers per meter. So therefore, there are 10 to the 10th angstroms per meter, and there are 10,000 angstroms per micron, a quite remarkable number. So this is about as thin as we can get. We can actually practically even do thinner than that. And let's take a look at threshold voltage for these conditions. So we have the threshold is equal, well, we could probably put this VFB on the other side. It's just an offset. And this is the gate, the band bending in the silicon. This is the voltage drop across the oxide. And I think we developed this formula when we were doing that business with the total band bending. Let's just put in the numbers. Flat band voltage minus about a volt. Excuse me, minus about a volt. For 10 to the 17th, we know, or we should be comfortable with the fact that the bulk potential is 0.42. This is 2 times 0.42. That's the total band bending in the silicon. And we just put in all these numbers. Q is 1.6 10 to the minus 19th. The doping 10 to the 17th. The permittivity of silicon, we'll be using this quite a bit, is about 10 to the minus 12th. That's a nice, easy number. And of course, this is 2 times 0.42. The C oxide, C ox is 10 to the minus 6. And we get a threshold voltage of 0.2 volts. So the first question we should ask, let's do a sanity check. These numbers we're assuming are pretty reasonable, and we get a very, very small threshold voltage. What does it mean? It means that this thing with no voltage, with 0 applied voltage, don't forget that the threshold voltage is a gate voltage. It is a specific gate voltage such that this relationship applies. And this particular structure with no gate voltage is 0 Botkas, nothing, would be in very deep depletion. In fact, it would be in weak inversion, because we only have to apply a tiny little positive voltage to bring this thing into strong inversion. But now let's ask another question. Suppose I want to know what this point is. This point here, this VT, for this particular example, this axis here should be, oh gosh, that's the wrong one. Oh, here it is. Okay. This axis here should be pulled way, way over. It should be right here. So the 0 point is right about there, just a little bit below the threshold voltage. And we are certainly in weak inversion. So I want to know what would be the gate voltage such that I start to go into inversion. This is pure depletion. This is weak inversion. Well, at that point, we know, or we should recall, that the intrinsic level just hits the Fermi level. So I want to know what happens when, and this is the condition, and this should be reasonable, that the band bending in the silicon is equal to not 2 times the bulk potential, but 1 times the bulk potential. And of course, that's exactly what we have here for the depletion, for the oxide capacitance. Excuse me. So instead of 2 phi-b, we have 1 phi-b. And there we work out that this, perhaps we could have called V1, but it's a specific gate voltage such that we just are entering into weak inversion. And that works out to be minus 0.44 volts. So with 0 gate voltage, we're certainly well into weak inversion. And if we put in minus 0.44 volt on the gate, we get into the point where we're right here. And this is actually negative. So this axis could be moved way over here. And this distance here would be from threshold to this point V1 would be about 0.46 volts. Okay, so last part of the session, I think we should review a little bit of where we've been, because we're going to next session get into some of the more complex and challenging mathematics of the MOSFET. So first we're going to compare the Schottky barrier and the MOSFET and take a look at those as rectifying junctions. And then we're going to summarize kind of a not very deep summary of all the structures that we've been looking at. So we start with the Schottky barrier. This Schottky barrier, metal, silicon, in this case, N silicon. I know it's N silicon because the bands bend up in the depletion region. Here it's heavily N-type in the bulk, and here in the depletion region it is less N-type, and it can go, in fact, to intrinsic. Notice, and this is very characteristic, whenever we have a metal, we're probably going to have sharp corners. And the reason is that inside the metal, in here, we have no electric field. It's field-free region. The voltage is constant, and if there's any charge, it is right at the metallurgical junction, and that is a surface charge. So generally we have sharp corners, and that is something that we try to avoid, but it's there. Whenever we have a metal, we're going to probably have sharp corners. So this is the metallurgical junction. This is where the field is the highest. We have 2 barriers. We have a variable barrier, phi-bi, which changes with bias. Forward bias, the phi-bi becomes reduced. Reverse bias, the phi-bi becomes bigger. Forward bias, the depletion region width, W here, becomes narrower, becomes smaller. Reverse bias, the depletion region width becomes wider. We also have a non-variable barrier, which does not depend on the bias. It's simply between the conduction band and the Fermi level. And we have 2 work functions. Here for N-type silicon, the metal work function is greater than the silicon work function. Of course, for P, it's the opposite. Okay, so now if we look at the MOSFET, which is this bad boy right here, we have an oxide interposed between the metal and the silicon. Again, this is N silicon. The bands bend up in the depletion region, which is right here, And in the oxide, the bands bend in the same direction. So here the slope is a negative slope for the potential, and here it is also a negative slope for the potential. The difference, however, is that in the silicon, the potential is parabolic. In the oxide, it is linear. And the reason is that in the oxide, there is, at least in theory, there are no charges. If there are no charges, the rho is 0, the electric field is linear, and the electric field is constant, The electric field is constant, and the voltage or the energy is linear. In the silicon, the depletion region, the rho, the charge density, the volume charge density is constant, the electric field is linear, and the energy is parabolic. So we've seen that quite a bit before. Notice again, for this particular structure, the metal work function is greater than the silicon work function. And just taking this one step further, in both configurations, there should be an S there, sorry about that, the total voltage drop at 0 applied bias. We can have a voltage drop across these structures at 0 applied bias, and that depends only on the work function difference, metal function minus the silicon work function, and that basically probably should be in magnitude, should be straight lines here, because it could be plus or minus, it really doesn't matter. However, in the metal silicon structure, metal semiconductor or Schottky structure, the voltage is only dropped across the silicon. In the metal semiconductor structure, the Schottky structure, in this particular case, I have positive ions in the silicon. These are ions, phosphorus. By the way, I think well, for me anyway, because I'm not very smart, I like to memorize this with a mnemonic. P is phosphorus. It's the quintessential donor, and P starts with, phosphorus starts with a P, and P is positive. So that's how I remember that the silicon contains positive ions, and at the surface, right here, the metallurgical junction, I have a negative surface charge. So in this particular case, the electric field is right to left in the negative direction. And in the MOSCAP, the same thing. I have two voltage drops. That's the difference. A voltage drop across silicon as well as a voltage drop across the oxide. So if we look at the electric fields, which is quite interesting to do, first of all, I should say that this particular, and I didn't do this on purpose, this particular structure shows the electric field being positive. Well, that's not what I have here. The electric field, since this is positive in the depletion region, and I have a negative surface charge density here, the electric field goes from right to left, so the electric field is actually negative. So this particular structure is for P silicon. So this would be for P silicon, and you can see that the maximum electric field is at the metallurgical junction. Here, however, in the MOSCAP, I have two voltage drops, one across the oxide and the other across the silicon. And again, this is for P-type silicon because the electric field is positive. And notice that the electric field is constant in the oxide. And that again is because the oxide is assumed to have no volume charge at all. And that's not quite the case, but in the ideal situation, we would like the oxide to have no charges, no ions. Okay, so this I'll allow you to read pretty much this thing on your own. This is kind of a basic summary of all the structures we've been covering, and I've highlighted 5 of them. There are some others which we haven't covered, but these are the 5 probably most important ones. I think one of the ones I'd love to cover, but it might take us a little bit far afield, is the thyristor, but I don't know if we'll get into that. Anyway, the 5 that we're covering here are the metal semiconductor, the Schottky, the p-n junction, the pin structure, that's 3, the iso junction, and finally the MOSFET. So in all of those 5, we take a look at a couple of different aspects. The energy bands and band bending in the metal semiconductor, in the Schottky barrier. There are 4 basic types. There are 2 rectifying structures, that is A here and C here, and there are 2 non-rectifying structures, B and D, and the difference between the rectifying and the non-rectifying is in the rectifying, the surface at the metallurgical junction always becomes closer to intrinsic. If it's N-type, it becomes less N-type. If it's P-type, it becomes less P-type. In the non-rectifying, B and D, at the surface, at the metallurgical junction, the silicon becomes more N-type if it starts out N-type, and it becomes more P-type if it starts out as P-type. And then we talk a little bit about barriers and electric fields in the Schottky barrier. This is all by way of review, the nature of the silicon surface, which is to say the interface or the metallurgical junction between the metal and the silicon. And so you can read all about that. And charge flow in forward and reverse bias. Again, there's charge flow in the forward bias when the barrier is reduced. There is reverse charge flow in reverse bias when the barrier is increased. And then we do exactly the same thing in the p-n junction. The same considerations. You see the differences. I hope I highlighted those with a reasonable degree of intelligence. Ouch. Hope that's the case. We'll see. You can read through that. Then the special cases, the one that I realize it's not only a very useful structure, but it's very nice and elegant to analyze when we stick an intrinsic layer between the P and the N type structures, and we get the pin diode. And I think we mentioned that this is a very important structure in microwave because the capacitance is reduced. So we went through that in quite some detail. And then the iso junction, where we have, for example, N plus N or P plus P, the same type but different levels of doping. So if we have different levels of doping, there still is going to be a barrier, but the barrier is going to have a different characteristic than in the p-n junction or the Schottky barrier. And finally, we take a look at the metal oxide semiconductor, which we've been covering, and so I don't really go into too much detail. This is the one that we're going to be tackling over the next couple of sessions in somewhat more detail. And it's a little bit challenging, but hopefully it'll be interesting. And we are going now to end. I'm going to skip through some of this. We'll be covering this next time before we get into the challenging mathematical part. And I end with a video clip, advice or league room, or this perhaps could be called advice for any groom, and I think you'll enjoy it, and we'll see you next time.
Philip, I want to tell you a story. And like all good stories, it starts like this. Once upon a time, there was a father. And in case you can't figure that out, that's me. This father had a wonderful little boy. He was very happy. But then one day he found out that his wife was going to have another baby. So I prayed, Lord, if it's your will, give me a little girl. And he did. I was the first person to hold her in my arms. And I looked at her and I said, Lord, make her like her mother. And he did. She was loving, giving, and so good and so kind. But then I realized I was getting left out. So I said, Lord, make her like me. And he did. She can drive a truck and a tractor. She can load hay and strip tobacco. You realize what you're getting? But at the same time, she was opinionated, and emotional, and hard-headed. So I said, Lord, that's enough of that. Make her like you. And he did. He gave her a desire to serve people. She loves people. She gave her life to being a nurse. She's brought people back from the dead. And she's held the hand of people and breathed their last breath. He gave her a heart for missions, and she's trekked all over the world. Pushed canoes up swollen rivers and laid on the floor while bullets whizzed outside so she could tell people about Jesus. But still something was missing. So I said, Lord, make her happy. And she made me. You see that look on her face? I never saw that until she met you. And I'm grateful for that. Today I'm giving you the best thing I have to give. And I just wanted you to know before I do that how hard me and God's worked to get it ready for you. So Philip, as I give her to you, I don't think you'll mind if I give you one little word of advice. Me and God's worked hard. Don't screw it up.